Hey everyone, think about your favorite playlist, your phone's contact list, even a simple deck of cards. What do they all have in common? Well, they're a whole lot more useful when they're actually sorted. Today, we are going to dive into one of the absolute simplest ways to bring order to chaos, an algorithm called bubble sort.
I mean, really, this is the fundamental question that every single sorting algorithm is trying to answer. It doesn't matter if you've got a list of numbers, a jumble of names, or anything else. The mission is always the same. Take a complete mess and turn it into a perfectly structured, organized sequence.
And right about now, you might be thinking, look, why should I care about the basics? My phone can sort 1,000 photos in like half a second. And you know what? That's a totally fair question. But if you really want to understand how that magic happens and honestly become a much better problem solver, you have to start with the fundamentals. Learning bubble sort isn't just about sorting lists. It's about learning to think like a computer.
So, let's get right into it. Let's pull back the curtain on our very first sorting method, bubble sort. The really beautiful thing about it is its simplicity. Seriously, you do not need a computer science degree to get the main idea, which makes it the absolute perfect place for us to start.
The definition here sounds simple, and that's because it really is. The algorithm has just one very simple job. It just kind of shuffles down a line, looking at only two items at a time, just two neighbors, and it asks one single question. Hey, are you two in the right order? If the answer is no, it swaps them. If they are, it just moves on to the next pair. That's it. You just do that over and over again, and eventually you've got a sorted list.
And this, right here, is exactly where it gets its name. With every single pass through the entire list, the next biggest value gets pushed all the way to the end, kind of like a bubble of air rising up to the surface of water. It's a really simple but powerful way to picture what's going on.
Okay, so theory is one thing, but actually seeing it work is another. Let's put this algorithm to the test. We're going to watch it work its magic on a small, totally jumbled list of numbers.
All right, here's our starting lineup. The numbers 5, 1, 4, and 2. Clearly, it's a mess. Our mission, if we choose to accept it, is to get these sorted from the smallest number to the biggest.
Okay, here we go. First pass. The algorithm looks at the very first pair of numbers, 5 and 1. It asks its super simple question. Is 5 greater than 1? The answer is a big yes, which means they're in the wrong order. So the first thing it does, it swaps them.
And there it is. Just one swap, and our list is now 1, 5, 4, 2. Now, it's not sorted yet, not by a long shot, but we've already made some real progress. The number 1 has already moved a step closer to where it's supposed to be.
Now the algorithm just slides over one spot to the right. The new pair we're looking at is 5 and 4. And again, it asks the same question. Is 5 bigger than 4? Yep, it sure is. So for the second time, we do another swap. And here's what we've got now. See what's happening? That number 5 is slowly but surely making its way to the right, inching closer and closer to its final sorted spot. We're almost done with our first full pass. We're at the last pair now, 5 and 2. And no surprise here, 5 is definitely greater than 2. So our algorithm does one final swap for this round.
And just like that, our first pass is done. But notice what happened? The biggest number in the whole list, the number 5, has bubbled all the way to the end. It's exactly where it belongs. Now, the list still isn't sorted, but here's the cool part. We can now totally ignore that last position and just repeat the entire process on the smaller remaining list. We just keep doing these passes until we can get through one whole pass without making a single swap.
So, we've seen the logic play out, step by step. Now, let's take a look at how this simple idea actually translates into real Python code. You might be surprised at just how closely the code follows the exact same logic we just walked through.
So let's just recap the core logic real quick. To make this work, we're going to need two loops. We need an outer loop that says, okay, let's start a new pass, and then an inner loop that does the real work of going down the line, comparing neighbor to neighbor, and swapping them. And we just keep making these full passes until we have one perfect pass where we don't need to swap anything at all. That's our green light. It tells us the job is done.
And here's basically what that looks like in code form. We're not going to get lost in the weeds of the exact syntax here, but you can see the structure perfectly mirrors our logic, right? You've got that outer loop for the passes, the inner loop for the comparisons, and then a little if statement that pulls the trigger on the swap. It's a direct one-to-one translation of the idea into code.
Okay, now this is where things get really interesting. For all of its beautiful, elegant simplicity, there is one major catch. Bubble sort is not what you'd call efficient.
And to really talk about efficiency, we got to quickly talk about a concept called time complexity. Now don't worry, in simple terms, it's just a way of measuring how much longer an algorithm will take to finish as you give it a bigger and bigger list to sort.
So bubble sort's time complexity is what we call quadratic. It sounds fancy, I know, but all it really means is that if you double the size of your list, the time it takes to sort it doesn't just double, it roughly quadruples. If you make the list 10 times bigger, it takes 100 times longer. It gets very, very slow, very, very fast.
And this quote from one of our sources really sums it all up perfectly. The bottom line is this: while bubble sort is an absolutely fantastic way to learn, that quadratic slowdown, which is caused by those two loops nested inside each other, makes it pretty much useless for sorting anything but the tiniest lists in the real world.
And that's the million-dollar question, right? If you're probably never going to use it in a real project, why on earth is it one of the very first sorting algorithms that everybody learns? Well, the answer is that its value isn't practical. It's educational. It's the perfect doorway into thinking algorithmically. It gives us a crystal clear, easy-to-understand example of what time complexity even means and why we should care. By truly understanding why bubble sort is so slow, we can appreciate just how clever and powerful more efficient algorithms like merge sort or quick sort really are. It's an absolutely vital first step on a much, much bigger journey.
And that kind of brings us full circle. You see, bubble sort is so much more than just a sorting algorithm. It's a perfect case study in one of the most fundamental trade-offs in all of technology: simplicity versus efficiency. Is it better to have code that's super easy to read and understand, or code that's just blazingly fast? The answer, as it almost always is it depends. And understanding why bubble sort is simple, but also slow, is the first step to being able to make those kinds of critical decisions for yourself.